Okay, let's get started. Hopefully you are making your way through the deliverables for your final project. A number of you have brought requests for additional functionality in PyroSim and other issues. So for every class from now until the end of the semester, I will try and give you a few hints and tricks and tips to help you with your project. So let's start with the issue about randomization in your project. So for some of you, you are trying to evolve your robot to be robust to something, right? Maybe you want it to move over rough terrain, you want it to do the same thing in multiple environments, and so on. So if you remember in the phototaxis assignment, we tried to make the robot robust in terms of phototaxis. So regardless of where the light source was placed, the robot would always go towards the light source, right? You might wonder why, whenever we were evaluating the robot, didn't we just place the light sources randomly? Why did we always place them in these four positions? Would it have been simpler to just pick a couple of random positions for the light source and test the robot's ability to find the light?
Are we preventing it from getting lucky?
Preventing it from getting lucky, exactly. So I won't, for the sake of brevity, I won't do all four environments. Let's imagine that we're going to evaluate every controller twice, and we're going to expose the robot to two different environments. We're going to pick the position of the light sources. Let's imagine that one single controller happens to just ignore the light altogether and uses touch information to move a body length or two into the screen. Let's imagine. Okay. So if we pick light sources at random, we might place one light source here and another light source here. What's the fitness of this controller? Not very good, right? It got extremely unlucky, right? So we would assign a very low fitness value to this controller. If, on the other hand, when we were picking the two random positions for the light source, we placed the light sources here, then this same controller gets a very high fitness value, right? It got very lucky. So depending on the random environments that we place this controller in, it might get very different fitness values, right? You might actually have a controller that is on its way to producing phototaxis. Maybe it moves a small distance towards the light source, but depending on where you put the light sources, you lose that potential good solution. So if you are doing anything like creating uneven terrain or trying to evaluate your controller in multiple environments and see how well it does in those multiple environments, I would suggest that you design those environments beforehand, like we did in the phototaxis assignment. You figured out the positions for the four light sources, and then every controller was evaluated against those same conditions, right? So you had a level playing field, even if your playing field is not actually level.
What about, I know this prevents like pure randomness, but could relative randomness be ideal?
What is relative randomness?
So you have the light block, say you want the light block to be 30 meters away.
Yep.
Could you just divide, so you have a circle around the robot that's 30 meters and you just divide it into 8 quadrants.
Okay.
You randomly put it into 8 quadrants. You run the generation 100 times, and you make sure that each quadrant is used an equal amount of times.
Right.
The overall position at any time is random.
Okay, so you somehow define quadrants, and then the light source has to be in these 4 quadrants. You could, right? So you're still introducing a little bit of randomness where it ends up, right? You're still running the risk that someone may get lucky. You're still reducing it somewhat because you're making the environment less random from the point of view of the robot. But my suggestion would be all controllers see exactly the same environment. Just make sure, again, like in the phototaxis assignment, make sure that even if your environments are deterministic, meaning the objects are always placed at the same position, they're very diverse, right? So there is no controller that is going to get a high fitness value in these 4 environments without exhibiting some form of phototaxis. Right? It's going to have to do well in at least two out of the 4 of these environments. Make sense? So just make sure, again, whatever you're doing for your final project, that individual controllers in your population aren't able to get lucky or unlucky, right? That with a relatively few number of environments, you're able to assess the fitness of your controller relatively well. Sound good? Okay, the other thing that most of you are going to wrestle with in the final project is coming up with a good fitness function for your controllers. And again, as we saw in the phototaxis experiment, it was pretty difficult to do so, right? It takes quite a bit to get a good fitness function. In the final project, we're not necessarily looking for you to come up with the best fitness function to select for exactly what you're looking for, but at least to walk us through 2 or 3 fitness functions that you tried. I tried this fitness function and it didn't work. For example, in the phototaxis case, I used this fitness function and it led to specialists. It produced robots that would only move towards one of the light sources and completely ignore the other 3. Right? So you show us that it doesn't work, and then I tried this other version and it worked a little bit better, and so on. Right? We're looking for you to show us that you're making progress in creating better and better fitness functions to select for whatever you're looking for. Okay, so how do you do this? It's not an easy thing to build up intuition for how to build good fitness functions. One way to think about this is, again, your fitness function is always going to be a function of sensor data, right? You can get whatever sensor data you want back from the simulation. What do you do with that sensor data? Let's imagine, for example, that I'm still working with the quadruped, and it has its 4 touch sensors, T1, T2, T3, and T4. And let's imagine, just for the sake of convenience, I'm going to get back all of the sensor data and I'm going to place it in one big matrix where every column in this matrix corresponds to one of the sensors in my robot. Let's say I've got the 4 touch sensors, and let's assume that I'm also going to have a ray sensor, which I'll just represent with Y. And you remember that the ray sensor actually has 4 components associated with it. The position sensor has 3, the X values, the Y values, and the Z values. The ray sensor has distance information. It'll give you back the length of the ray emitted by the ray sensor. And it will also give you back a red component, green component, and blue component of whatever that ray sensor hits, the color of the object that the ray sensor hits. If you remember back to when we were playing around with the ray sensor, when it would hit something, the color of that ray would actually change. When the ray hits the ground, it reports black, so the ground is actually black from the point of view of the ray sensor. So here we go. Let's assume I now have a quadruped that has 4 touch sensors and 1 ray sensor, and I pulled out these 4 components, or these 4 vectors, that are returned by the ray sensor. What was the distance of the ray at every time step? And if it hit something, what was the color of that object? Again, if it doesn't hit anything, I think these are all 0, 0, 0. So each row corresponds to a sensor. Each column corresponds to a sensor. What does each row represent in this matrix? The time step, right? So the first row, these are the values of these 8 sensors, if you like, at time step 0, all the way through to T subscript uppercase T. So I use uppercase T just as shorthand for the final time step. Okay, so once you have all this information, how could we make different kinds of fitness functions? Let's imagine that you want to ignore what the robot does for the first half of its lifetime, and you only want to compute fitness based on what it does in the second half. Where is that information in this matrix?
T sub big T over 2 greater than T sub big T over 2.
Right, lowercase t, time step subscript t divided by 2. So we're just taking the bottom half of this matrix, and then I'm extracting some values from this. So if I were to do that, then it doesn't really matter what the robot does in the last half, or in the first half of its lifetime. We're ignoring that, right? In the assignments, you were actually just using the value of the sensor at the very last time step. Let's imagine that you wanted to select for a robot that was hopping, meaning that it should sometimes have all feet on the ground and sometimes have none of its feet on the ground. How would you use this matrix to select, to create a fitness function to select for hopping?
There would have to be time steps where all 4 touch sensors are reporting 0.
Right, so we're looking for subsets of a row that are all zeros, or what else? Or all ones, right? So if it's hopping, some of the times all 4 feet are off the ground, and sometimes we're looking for subsets of rows in which there are all ones, right? So we could create a fitness function that returns an integer, which is the number of rows that match this pattern, either all zeros or all ones. Right? Let's imagine you actually did that. You evolved the quadruped with these sensors and that fitness function. What do you think you would get? Would you get hopping? You'd get a robot. Maybe. You might notice that, of course, at the beginning with random controllers, they're hopping around quite a bit because sensors are affecting motors. But it's probably easier for evolution to produce a robot that stays still and has all 4 ones at almost, or if not all rows, rather than what you want, which is hopping, right? I think we mentioned this somewhere along the line. This is called perverse instantiation. So you imagine some behavior you would like instantiation. You imagine some behavior you would like your robot to perform. You come up with a fitness function that you think will select for that behavior, but it turns out that there is some perverse instantiation of that fitness function which doesn't produce what you want, right? I know some of you have already experienced that in your final project, right? Write it down, document it. That's a good first step towards what you actually want, right? So if your final project actually is hopping and you say, I used this fitness function and actually it produced a robot that never moves. Now I came up with fitness function version 2.0, which hopefully will do a better job of selecting for hopping. How would we change our fitness function from this to select for hopping and penalize for robots that are just standing still?
I guess then we could add another sensor that's that try to penalize if the robot doesn't move to anywhere else, like a position sensor.
Could do that. You could add a position sensor, and you could do something that looks at the change in the position sensor, right, and penalizes for amount of change. You could add a position sensor here and compute the standard deviation over the position sensor. How much movement is there, how much delta, how much change is there in the position sensor? Right? You could do something like that would penalize for standard deviation.
You could reward robots for having count of all zeros being close to the count of all ones.
Exactly, right? We could maximize for the number of rows like this and then minimize the difference between the number of rows that are all zeros and all ones. That's it, right? That may or may not produce hopping. There may be some other perverse instantiation of that, but that's sort of what we're looking for in the final project, right? You tried fitness function version 1.0, didn't work. Based on what you saw, you added a term to the fitness function to select against it. You remember when we talked about the passive dynamic walker? They had that long fitness function where they're multiplying a whole bunch of things together. The first term was distance, and all the other terms were penalizing all the different forms of the ministry of silly walks that you might get, right? Your fitness function might look similar by the end of the semester. Okay, so again, I would suggest if you're not quite clear about how to come up with a fitness function or design an experiment to evolve the behavior that you want, sit down with pen and paper, draw a matrix like this, and sort of think about what sorts of computations could you perform on this matrix to produce a fitness function to select for what you want. Don't overthink it. Come up with version 1.0. It might be relatively simple. plug it in, see what you get, add in another term, evolve it again, and back and forth, back and forth. Make sense? Okay, any other questions? No? Okay, so let's carry on. Let's return to lecture. We're working our way through a short segment here on collective robotics. So ultimately, if we're going to deploy robots into the real world, there are certain tasks that are going to be beyond the ability of any one robot. So we would like to train our robots, or maybe evolve our robots to coordinate their actions and work together to do something that would be beyond the ability of any one of them. Okay, so we were working our way through an early experiment in the field of evolutionary robotics that looked at this. They used a very, very simple two-dimensional simulation. They had this virtual gazelle that was running around this infinite donut or toroid. The gazelle always moves faster than the 4 lions. Just to remind you, the gazelle's behavior is pre-programmed, which is always to move away from the lions, and we're going to evolve the behavior of the 4 lions. We ended last time with this slide, which was visualizing the fact that the investigators in this case used genetic programming to evolve controllers for their lions. And genetic programming is a form of an evolutionary algorithm in which the genomes are encoded as trees rather than matrices or vectors. Right? I ended last time by showing you, by coming up with a couple of potential genomes. So we imagined a tree that was a single node, this node gazelle. That node, every node in a tree returns a vector, and that vector is the direction that the lion is going to move in the next time step. Right? So a lion that always moves 1 unit length vector in the direction of the gazelle, how well is it going to do at catching the gazelle? Not very well, right? Because it moves 3 times more slowly. If we took our 4 lions and we each gave them this 1 node tree, how well would those 4 lions do at catching the gazelle? Not very well, right? They're all going to sort of converge behind the gazelle and chase the gazelle, and the gazelle will easily elude the lions, right? So that none of those simple trees are going to work very well. So evolution is going to create more complex trees for the lions. And if any of those more complex trees allow the lions to get closer to the gazelle or possibly catch it, they're going to get higher fitness, right? So let's make a slightly more complex tree. You can see that these 3 nodes up here require 0 arguments. So these are potential leaf nodes in the tree. And all the rest of these potential nodes here require arguments, and they're vector operations, right? So remember, when we're doing genetic programming, we want to start with creating a population of trees, and each one of those trees is going to be used by the gazelles, and by the lions. We'll see how well the lions do. So let's create a tree at random. Let's reach into a bag that contains all of these potential operators and operands. Let's imagine that I pull out at random the plus sign, which requires 2 subtrees. At the moment, these 2 arguments or 2 subtrees are empty. I reach back into the bag again, and let's say I pull out gazelle here. Gazelle has 0 arguments, so I'm done here. I go to this empty node here, reach back into this bag, and select one of these nodes at random. And let's imagine that I grab the random direction node, which also has 0 arguments. So I'm done creating this tree. If I take this tree and I drop it into each of the 4 lions, at each time step, this node is going to return a vector that connects the lion with the gazelle. This node is going to return a vector, which is a random vector. Those 2 vectors are added together, and this node returns a vector, which dictates the movement of the lion at the next time step. Did you have a question?
I was confusing the random direction and random.
Oh, okay. Okay, so how are our 4 lions equipped with this controller going to do in capturing the gazelle? Still not very well, right? Our lions are having a hard time here. Okay, so I think you get the idea, right? We're creating these trees at random, and then we're going to evolve these trees. So perhaps these lions do slightly better than lions that just have this node. They're still not going to do very well, but maybe they do slightly better. So this tree survives, and the other tree, the one node tree made up of gazelle, dies off. This tree produces an offspring like itself, but this node gets mutated, so we reach back into our bag at random and we grab something else like if dot. This requires 4 arguments, so we need to fill in those arguments at random, and so on. So we have a child which is similar to, but not identical to the parent. Okay. So let's have a look at some of these other possible nodes in the tree. This one returns a random vector. This one returns a random vector in the same direction, but it modifies. It takes the vector, that's the single argument, and changes its length by a small random amount. This one inverts the magnitude of the vector that it's receiving. This one, if dot, is interesting. This one takes 4 subtrees. Remember that each of the 4 subtrees at every time step are returning a vector. So we take the dot product of the first and second. We take the dot product of the vectors returned by the first and second subtree. And if the dot product of those 2 vectors is greater than 0, we return the vector returned by the third tree. If the dot product is less than 0, then we return the vector returned by the 4th subtree. So you can think of these trees, if you like, as computing vectors down in the leaf nodes, and then their vectors are flowing up towards the root of the tree, and those vectors are being transformed as we go. So no matter what tree we construct, at every time step there is always one vector that's returned by the tree, which is the direction the lion moves in the next time step. Okay. Is there a combination? Can you imagine some combination of these vector operations and operands that will give you a team of 4 lions that captures the gazelle? I'm asking you to simulate evolution in your head here. How do you think the lion, the pride of lions, will do?
There's a way.
You think there's a way?
Probably going with 4 lions and on a 2x2 plane. You should be able to utilize the invert vector magnitude and rotate 90 degrees to get a decent flank off on this gazelle.
Maybe it's possible. Maybe, right? Let's see. Okay, we're going to see some lions evolved with these GP, genetic programming trees, in a moment. They did a number of experiments in this paper. The first experiment was using these operations and operands. In the second experiment, they added in 4 new possible leaf nodes. And these are, you can think of these as additional sensors. So for example, nearest will now return a vector from the lion nearest the gazelle to the gazelle. So let's imagine the gazelle's at the back of the room. I'm a lion, but one of my fellow lions is up front and is closer to the gazelle than I am. So we got the gazelle in the back of the room. I'm a lion here. There's another gazelle, another lion closer to the gazelle. I execute a tree that contains just one node, nearest, which is the vector that connects that nearest lion to the gazelle. I'm going to move along that vector. Maybe not the best thing to do, but I can sense the vector that connects another member of the pride to the gazelle. There is another vector which connects the lion, meaning me, to my nearest neighbor, which is the lion that is closest to me. I am one of the 4 lions, so there are 3 other of my lion colleagues that are out in the virtual Serengeti. which is the vector that connects me to my closest lion. That's another possible operation that I can make use of. It's another sensor, if you like. As I'm moving around, I always can see a vector that connects me to my closest lion. R lion means I take a line and I start marching clockwise from me, the direction that I'm facing. And the first lion that I hit in this clockwise sweep, the vector that connects me to that lion, is returned by R lion. I can also use L lion to detect the lion that is on my left side. So these three here are known as deictic sensing, meaning they're relative to me. When the lion executes right lion, it's sensing something relative to itself, the lion on my right. Another member of the pride, another lion that executes exactly the same controller, our lion, it will have a different vector because there will be some other lion that is to its right. Right? So deictic sensing is basically relative sensing, right? Who's on my right? Who's on my left? Which of the members of my team are immediately in front of me or behind me or closest to the gazelle or so on? Which pack of lions do you think did better? The lions evolved with these controllers or the lions evolved with this set of operations plus these sensors? Probably these, right? This is probably going to help. Okay, so we'll look at the results from these two experiments in a moment. They did a third experiment where, again, they started with the base set here and then added name-based sensing. So now there are 4 additional sensors, L1, L2, L3, and L4. And if any one of those is in your controller, for example, L1, it will return the vector that connects lion 1 to the gazelle. If I'm lion 1, it's the vector that connects me to the gazelle. If I'm lion 3 and lion 1 is over here, I execute L1, which is the vector that connects lion 1 to the gazelle, and I, L3, have that piece of information, right? So this is name-based or absolute sensing. Which team of lions do you think did better now? This team of lions with this plus this, or the third team of lions, which is this plus this? Why this?
Because it'd be easier for them to coordinate.
Exactly, right? So if you remember back to the title of this paper, it's the evolution of coordination, right? Like real lions, our virtual lions are going to have to evolve some way to coordinate their actions, right? So they need to have information not just about what they're doing or what the gazelle is doing, but what their fellow members of the pride are doing. Okay, let's add in some additional elements to this experiment. Some of you are actually trying to evolve not just a single robot, but multiple robots. And it's tricky, right? How do you do this? If you have 2 robots or 4 robots or 10 robots, do you have one genome for all of your robots, or do you have a single genome for each robot in your team? There are different ways to do this. So this is a good experiment for you to draw some inspiration from. The simplest thing to do is cloning. So you have your genome here represented as a tree, right, which is performing these vector operations. You take that genome and you clone it into each of the 4 lions. So all of the 4 lions have exactly the same controller. When we drop our 4 lions and the gazelle into the virtual Serengeti, do all the lions do exactly the same thing? Why not?
Well, there's the if statements and the sensor input will be different based on what the gazelle is.
The sensor information will be different, right? All the lions in the cloning case, they're all using exactly the same controller, but they sense the world differently depending on their position in the Serengeti plain, right? So they can still do different things, but they're using the same controller. Okay, that's cloning. The other thing you can do is free breeding, where now the genome looks like this. you have a larger tree where the root node is empty, and then you have four possibly different subtrees where each subtree controls an individual lion, right? So you still have one big genome, but this genome is encoding the control strategies for each member of the team separately. So in your case, you have not a tree, but you have a matrix of 32 synaptic weights for your quadruped. If you wanted to evolve a pair of quadrupeds to do something together, you could just create a list or a dictionary, if you like, a genome that contains two matrices. Right? One labels the synaptic weights for quadruped 1, and the second matrix labels the synaptic weights for quadruped 2. Okay, so in this little cartoon here, we have a genome for the team. Remember, we have a population of genomes, so we actually have a forest, right? We have a population of trees. When we're producing a child in free breeding, what we can do is create an empty root node, so we're creating a new child. Let's imagine that these three trees survived in the population. They produced slightly higher, more fit teams than some other genomes which died off. We take the subtree for lion 1, we make a copy of it, we mutate it, and we plug it in as the controller for lion 2. We pick another subtree at random from another genome, we copy it, we mutate it, we plug it in somewhere else, and we keep going until we've created 4 mutant subtrees, put them together, and we now have a new child genome. That's one possibility. Third and final possibility is restricted breeding. So same thing we saw up here. We still have one genome, which is encoding strategies for the entire team. We have 3 genomes which have survived. They're combining their genetic material to produce a fourth, a new team down here. I'm sorry, there's a 4th genome here. I ran out of room to draw it. When we're trying to create the new strategy for lion 1, we only pick a lion 1 subtree from one of the parent genomes, copy it, mutate it, plug it in, and so on. So it's restricted, meaning a parent can only donate a subtree from from one lion to the same lion. Make sense? Okay. All right, let's start to look at some results now. They did a total of 1,200 evolutionary runs. They had 9 possible experiments they could run because we have 3 different breeding regimes and we have 3 different sets of sensors that we're going to evolve our lions for. So 3 times 3 gives us a set of 9 experiments. For each one of those 9 experiments, they did 100 independent evolutionary runs. They wanted to see, on average, how well could they evolve teamwork and coordination in these 9 experiments. And they did an additional 10th, 11th, and 12th control runs. First one was 1 lion with an evolved behavior, 1 randomly moving lion, and 4 randomly moving lions. These 3 control experiments, as you can probably imagine, these are more like sanity checks, right? They're not going to expect these lions to do very well. These lions up here, regardless of which of the 9 experiments, should be able to do better than these experiments. Right? If not, something's probably wrong. Okay, here's some statistics about, some experimental settings they used. So for each one of these evolutionary runs, they ran it for 51 generations. Why 51 and not 50? They start with their first generation, which are just random controllers, and then they perform 50 additional generations. Population size 500. These trees could grow to have a maximum of 70 nodes. They never allowed trees to grow deeper than 17 levels. They used quite a bit of crossover, just a little bit of mutation. Every time they took an individual tree and they were about to evaluate its fitness, they placed the gazelle and the lions randomly, and both the gazelle and the lion were allowed to move 15 times. After those 15 movements, they computed the fitness of the lion team. Remember, we're not assessing the fitness of any individual lion. It's how the team did as a whole. If there was at least one lion that was less than 1 unit distance from the gazelle, that counted as a capture, and that lion team got a fitness of 0. So in this case, lower values are better. If the lions failed to catch the gazelle, fitness was how close did the nearest lion get to the gazelle. Makes sense, right?
So is randomness good in this one, or are we allowing the lions to get lucky and kind of like spawn on top of the gazelle?
That's a good question. They may have actually, they probably should have done this multiple times. It's possible that they could have put the lions in some initial random configuration that allowed the lions to do pretty well. That's a good point. They should have probably done this multiple times. Okay. All right, ready to see some results? Okay, I'm going to walk you through this slowly. Again, unfortunately, this was a very early experiment, so they made no actual animations, which would have been a shame, because we would have actually been able to probably to see any coordination if it did actually evolve. Let's have a look at how this works. Let's have a look at the 3 control experiments first. So they're reporting, remember they did 100 runs for each of these 12 experiments. They're reporting the average fitness of the lion team across the 100 runs, and they're reporting the fitness of the best team evolved in these 100 runs. Okay, so one evolved lion does not do significantly better than one random lion, right? Which is what we were expecting. Now, it doesn't matter what that one single lion does, it's probably not going to be able to catch the gazelle. So no real difference here. We'll save this question for a moment. 4 lions do better than 1 lion, regardless of whether it's an evolved lion or a random lion. Why do 4 do better than 1, even if they're just moving randomly?
The odds are the gazelle's going to be closer to one of the lions than the others.
Exactly. They're moving around randomly. The gazelle has much less room to maneuver in, right? Okay. Clearly, though, in the 9 experiments above, if you look at the averages there, even the best, you can see that the lions in all 9 cases did better than the 4 random lions, which tells us that evolution actually was doing something in all of these 9 experiments, right? There was some combination of these vector operations that would allow the lions to coordinate their action and get closer to the gazelle compared to the 4 randomly moving environments. Again, this is a good, there's a good piece of knowledge here for your final project. So again, we're not necessarily looking for optimal behavior. We're looking for you to prove that whatever it was you evolved your robots to do, they did better than random, right? So it's easy, relatively easy to show that evolution is doing at least something. Okay. So let's have a look at this. For clones, remember clones means that each of the 4 lions is running exactly the same control strategy, which is over here. For clones, name-based sensing was worse than deictic sensing. So here's name-based sensing. It actually did worse than deictic sensing. That seems a little strange, right? So let's just remind ourselves what we're looking at. We're looking at cloning here. Each of the 4 lions is running exactly the same control operation. And in name-based sensing, they have this information. Why did the clones do so poorly with name-based sensing compared to deictic sensing? I'll give you a second to think about it. So the clones, in the case of name-based sensing, they're basing their strategy on vectors that say things like the vector that connects lion 1 to the gazelle, the vector that connects lion 4 to the gazelle.
I still don't understand why name-based sensing is better than deictic sensing.
It's not in this case.
In most, though.
We will look at the cases where it's better. Why is it worse in this case? Let's focus just on the clones for a minute.
Did each thing evolve individually instead of as a pack? So it wasn't really optimizing the group performance, but more each individual line's performance.
Possibly. Do you have an idea?
It's selecting those name-based ones at random, so it could be selecting less useful ones. Whereas the didactic are, like in terms of sweeping,
It's relative to self, right? Okay, so let's think about this, right? We have a team of 4 lions. I'm one member of the team. We're clones, which means we all have exactly the same. We all have exactly the same controller. Let's imagine that controller is made up of a single node, which is L1, right? Let's imagine that I'm lion 3. I'm L3. So I run this controller, which gives me the vector that connects lion 1, which is over there, to the gazelle. So I move along that vector. What does L1 do? Same thing, right? So L1 is over there. It is also running this controller L1, which in its case connects it to the gazelle. It moves towards the gazelle, right? Which is maybe not such a bad thing to do. Do I move towards the gazelle? If I'm running this, I'm doing something else, right? So this might do well for one or a few of the lions in the pack, but not for the other lions in the pack. We're all being forced to do the same, use the same thing. But the lions did better, the clones did better when they were using deictic sensing in this situation. Why? So let's imagine that we're all now running this node, which is right lion. Move based on my connection to my right-hand lion. Why is that better? Why is deictic sensing better in this case? We're all moving in different directions, right? My right-hand lion is going to be different from your right-hand lion, right? So evolution can still diversify the behavior of the lions, maybe in a good way, right? Maybe we managed to all circle around the gazelle because we're all moving based on what our right-hand neighbor is doing, possibly, right? So there start to be these interesting interactions between the way in which we're evolving intelligence for the team and the way we force the team to see the world, either in absolute terms, in name-based sensing, or deictic sensing. Okay, if you look at the 9 averages in this table here, the restricted breeding team did best with name-based sensing. That was the best combination overall. Why? So just to remind you, here's restricted breeding, and then here's name-based sensing.
Each line was able to specialize and have a specific role.
Exactly, right? So it's evidence showing that specialization, first of all, it's the best thing to do in this situation, and evolution was able to discover that. Right? Now again, it's such a shame they don't have an actual animation of this. We can't actually see what lions specialize to do what. Anybody know what actual lions do? Which is they do specialize.
I don't know about that.
Okay.
I had a question about the name-based.
Sure.
So are you saying after evolution they would be L1 is the chaser, L2 and 3 are the flankers, and they would come with those roles?
Absolutely, right? Because we're dealing with restricted breeding, right? So let's say L1 actually is the chaser, right? So this subtree here is evolving to head straight towards the gazelle, let's imagine, right? The other subtrees are evolving to do something else, which should probably be don't go towards the gazelle. You'll mess things up if you do. do something else. I don't know what they do, but do something else. And do it based on what L1 is doing, right? And you know what L1 is doing if I'm L3 because I have L1 available to me. So I can, in essence, watch what L1 is doing and modify and as a specialist, do what I'm supposed to be doing, but do it based on what I see L1 doing. Or also what L2 is doing and L3.
Kind of like the ghosts in Pac-Man, they have specialties as well.
Absolutely.
So like, I think it's like the red one will move directly towards the pink one moves around randomly, and the other ones do
Whatever they do.
Yeah.
Yes, that's right. Exactly. So again, specialists, right? If you want to work as a team, in a lot of situations, it makes sense to specialize. If everyone tries to do the same thing at the same time, usually there is coordinated frustration, right? You all immediately chase after the gazelle, and you end up collectively making things really easy for the gazelle, right? Better to specialize and spread out and do different things. Make sense? Okay. Could we do even better? Could we come up with a 13th experiment in which we give even more information to the lions? If you were to continue this experiment, what else might help the lions here? Even in the case of restricted breeding and name-based sensing, what can the lions still not know in this situation?
The size and shape of their environment?
The size and shape of the environment. So yeah, we could make the environment more challenging and complex. We could put in other kinds of sensors. What else? What else might it be useful for the lions to do? Even in this simple case, I'm lion 3, and I know what L1, I have the vector that connects L1 to the gazelle. What other information might be really useful to me in that instant of time?
Distance between lines, so? Or is that included?
You have that information, right? So if I have that vector, L1, remember I have all these vector operations that I can manipulate, right? I can compute the length of that vector. I can manipulate it, or evolution can produce a brain for me that manipulates that information. So I still have that. What am I missing?
With the ability to change line names based on initial position?
Possibly, right? So maybe we could switch roles, right? That's something. Let's go back to this situation. I'm L3, L1 is up there. I have the vector that connects L1 to the gazelle. What would I really like to know in this instant of time? If you're playing a team sport, right, and you've got your fellow players on the field, and you can see where they are, you can see where the other members of the team are, in that instant, what would you like to know about the state of play? What their fellow lions are going to do next, right? You have the vector that connects L1 to G, but you don't know in restricted breeding what L1 is going to do at the next time instant, right? You also, if you're playing a team sport, it's also good to know what your fellow players are going to do. Maybe you've discussed it in the huddle before the play is made. What other options are available to you if you're in the midst of a play in a team sport and you'd like to know?
I thought name-based breeding allowed the lions to know what the other lions were doing.
It lets you know about their current state, right? So name-based sensing says, you know the vector, you can see where basically you can see where L1 is relative to G. You can see it in the sense that you get back the vector that connects L1 to G. But you do not know what L1 is going to do next. In restricted breeding, going back to this example, I'm lion 3. I'm executing this control strategy here. I have no idea what's in here or what the lion is going, how the lion is going to behave based on this. So you're in the midst of a play in a team sport, and you're all about to start moving. What's the possibility?
The goalie tries to score.
The goalie tries to score, possibly. Okay. How might you know that? Again, you might have decided in the huddle or whatever it is beforehand, the scrum, I don't know, pick your sport.
Talk to each other.
Talk to each other, right? You might talk to each other, you might call it out, right? Or you might signal somehow by looking at each other, right? So in lecture 21 here, we have been looking at coordination, right? We're going to move on now to communication, right? If you really want to coordinate action over a very large, diverse group, you can only get so far without language, right? Without communication somehow. In the Twitch Plays Robotics project, we already looked at language, but that was robots trying to learn English. They were trying to learn human languages. In lecture 22 now, we're going to look at robots that are trying to coordinate their actions, and they devise their own language amongst themselves to do a better job of coordinating their actions. Okay, so we're going to look at literally the evolution of communication. Okay, here we go. All right, again, this is a relatively old experiment in the field. Actually, it predates evolutionary robotics. So these are sort of disembodied agents, kind of like the lions and the gazelles. And again, this is an explicit study of the evolution of communication. This is the first time we've actually seen gendered agents or robots. We have male and female agents in this case. Like the previous experiment, the male and female agents here inhabit this infinite toroidal world, so they're on this donut. This toroid, however, is discrete rather than continuous. So the agents occupy individual cells on this surface, and they move from one cell to the other. We have a total of 40,000 possible squares, 200 times 200. At the beginning of the experiment, we sprinkle 800 female agents and 800 male agents throughout this grid. And the males and females have different sensing and actuation capabilities. So the females are deaf. They're immobile. So once they're dropped in a cell, they can no longer move, but they can signal. And these larger squares are representing the area in which they can signal. So the females, as you'll see in a moment, can emit signals into their environment, but it can only be heard by males that are within the signaling radius of a female. Males are blind. They can't see the females, but they can hear signals. They cannot signal themselves, and they are mobile. Okay. So far, so good? Male and female agents have the same cognitive architecture. So cognitive architecture means the number of neurons and the number of synapses. But other than that, their networks are very different. Let's start with the female network up here. It's got the structure we're kind of used to. We have an input layer, a hidden layer, and an output layer. The input layers, actually for both the females and the male, is binary. The input layer for the female reports the position and orientation of the closest male in her visual range. So in this case, this female has no males in her signaling range, so her input layer would be all zeros at this particular instant in time. This female would be able to detect by the setting of ones and zeros at the input layer that there is a male that is southeast of her and facing south. Northeast of her, what kind of sensing are we talking about here? Not name-based sensing. Deictic sensing, right? So the females are sensing males relative to her position, right? Where's the male relative to me? This female has two males within her visual range. She can only see, quote unquote, the male that is closest to her. So her input layer would signal that there is a male to her southwest, and that male is facing west. Okay. So we have the input layer set. We would propagate a signal through to the output layer. We're going to evolve the synaptic weights as usual. And again, there is the neurons at the output layer are clamped to binary values, so we're going to use a threshold function to set them to be 1 or 0. The values arriving at the output layer for the females are not sent to the female's motors because she is immobile. Instead, this is her mating call. So she sends this signal, she sends this binary vector out into her signaling radius, and any males that are within that signaling radius, that song arrives at their input layer. So the male network takes as input any song heard by a female. If a male is outside, if a male, for example, is outside of a female's signaling radius, what do you think arrives at the input layer of this male's network? All zeros, right? The male doesn't hear anything. Okay. The signals propagate through to the output layer for the male's network. Here we use a different threshold function that squashes the values, or actually expands the values to integer values. There are 4 output neurons, which correspond to 4 possible actions that the male can take. Stay still, move forward, turn left, or turn right. Whichever of the 4 integers down here is largest, that's the action that the male performs. So in this cartoon here, this particular male hears 1, 0, 1. These values arrive at its output layer, and it turns right in response to the heard female song. So far, so good? Okay. Okay, so as we're going to see when we start walking our way through one of these experiments, the males move around at random on this grid because we're starting with random controllers for both the males and the females. If a male happens to move into the cell occupied by a female, they reproduce, and they produce 1 male offspring and 1 female offspring. The male, ironically, there's a lot of talk about mating in this experiment, but there's no actual mating that goes on. The male's network is copied, or the synaptic weights associated with the male network are copied and mutated. That becomes the male child. The female child is a mutated copy of the synaptic weights from the female's parents' network. Make sense? Okay. We take those 2 new agents that we've just produced, the male and female. We pick a female at random somewhere else on the grid, kill her off, and she's replaced by the female child. We find another male at random in the grid, kill that male off, and replace it with the male child. We take the original male and female parents, and we move them to random positions on the grid. Rinse and repeat. So there's a number of things that are different in this experiment from what you've seen before. First of all, that we have gendered agents, and we also don't have a traditional evolutionary algorithm here. Everything you've heard up until this point, every evolutionary algorithm, we've assumed we have a population of controllers. We evaluate the fitness of each controller in the population. Controllers with low fitness die. Controllers with higher fitness produce offspring. There are no generations here. There are just males moving around randomly, females signaling randomly. If they ever manage to connect, they produce 2 offspring, and those 2 offspring kill off 2 other individuals somewhere in the grid. A little bit closer to biological reality. Right? Okay. So what happens? All right. Again, this is a pretty old paper, so no fancy graphics here. We're going to do everything with tables. I'll walk you through how to read these tables. In this first experiment we're going to look at, they used mating songs that were 3 binary digits long, which means that the female output layer had 3 neurons, and the male input layer had 3 neurons. Okay. So we're working with binary values, so we've got 8 possible signals that the females can emit. We're creating 800 random females, so they tend to produce these 8 songs on average. We also have 800 males. What do they tend to do? 25% of them, when they were within hearing range of a female that was emitting this song, 25% of them moved forward, 38% of them turned right, 9% of them turned left, 28% of them stood still. In the 800 random males that happened to hear a female emitting this signal, 19% did this, 20% did this, 31% did this, and 30% did that, right? Which is what you would expect.
Would the top one with the 3 zeros be no song, or would that be?
It's still a song. The female can emit 0, 0, 0. That's right. This is, each row here corresponds to what did males tend to do when they heard that song. It doesn't report what they did when they didn't hear the song. Okay, these numbers are going to start to change as we march through this experiment. This is what they're reporting at time equals 100, which means all 1,600 agents did whatever they do 100 times, right? So there's no generations here, right? Remember, because breeding occurs or mating occurs when pairs meet up. So we can't report our results generation to generation because there are no generations. So this is after 100 actions performed by the 1,600 agents. What do you think is going to start to happen? Is it going to stay like this? Is there going to be a uniform distribution of male actions in response to female signals? Why not?
The population will start to overtake the world they're given, I guess.
Okay.
And
They're going to start.
respond similarly to similar songs.
They're going to start to respond. The males are going to start to converge on certain actions in response to certain songs. Why? Here you have males that are just moving at random. Why is that not the best thing to do?
Eventually, the males that have moved at random and have gotten their ability to keep living,
Yes.
keep doing that one random action, and if that random action keeps succeeding, that will take over.
Possibly. If you're a male agent in this environment, what's the best thing you should be doing? Or generally speaking, what is the thing you're supposed to be doing? Finding females. Is moving at random the best way to do that? Probably not, right? You'd like to move non-randomly. So let's see what happens. This is what happens at time step 5,000. As you will see as we go through this experiment, there are a lot of similarities between these male agents and human male behavior. I don't know if the investigators did this on purpose, but here you can start to see our male agents doing something that human males tend to do, some of us at least. What's happening? Let's go a little bit further forward. What's happening at time step 7,500? All the males just move forward. Doesn't matter what signal they hear. If they hear no signal, just go forward, right? Again, you can read into that whatever you like. At least in this simplified environment, that's at least a better strategy than moving at random. Why? It's not that much better, but clearly better.
You're not hitting the same coordinates that have failed.
You're not hitting the same coordinates, right? So if you're moving at random as a male, remember that there are 4 things that the male can do. 3 of those things keep you in the same location. Since females don't move, you're guaranteed to not find a female at the next time step if you stay in the same cell. Best thing to do, at least starting from random, is move forward. Okay. As you can imagine, this is not the end of this experiment. Turns out there are better things to do. This is the state of play at time step 15,000. What's happening now?
They learn to, I don't know if it was female or male, but like when a female emits a certain signal, then they'll turn right or left.
Exactly, right? So most of the males at this point, most of the 800 males now are turning right when they hear 101 and turning left when they hear 110, and all the rest of the time, if they hear the other 6 signals or hear nothing at all, they move forward. At the previous point in time, what did these signals, what did these female signals mean?
Nothing.
Nothing at all, right? The females might have meant them to mean something, but if the responder can't hear the meaning in the signal, it's worthless. What does 101 mean now?
On your left.
It means
On your left.
on your left, right? Or at least turn left. Okay, so in this case here, the females are also evolving a signaling strategy. They're not always emitting the same signal. If a female always emitted 101, what would happen to the males that entered her signaling territory?
Get stuck.
They get stuck, right? They just keep turning left, right? So the female is going to emit these signals selectively. Remember that she can sense where the males are relative to herself. So in this case now, the females are going to emit this pattern when the male is on the same row or column as the female. Why does that make sense? So there's a female sitting here. There's a male to the north of her that is moving to the east. Enters top right relative to the female, starts moving, and hits the column, the same column as the female. The male is now immediately to the north of the female. So they're on the same column as the female, and she emits 101, which causes the male to turn left. So now the male is facing not east anymore, but south. What does the female signal at that point? Anything else, right? Any of the other 6 signals or nothing at all, right? So what happened in this particular experiment is the females were very selective about when to signal, and they deflect or modify the male's behavior just at the right point in time and space, right? And then rely on the males, these males, to do what they tend to do, which is move forward. So here's a little visualization of this. At 15,000, the females were emitting that signal at those situations. As time continued, the females evolved to use the same 2 signals in greater and greater situations, right? So maybe the female only emitted the signal when the males entered the same row on her left-hand side. Eventually, the females evolved to emit the signal in more and more of these shaded regions, which would mean in essence that she'd be able to capture more males that are entering her territory from different locations and moving through the territory at on different headings. Okay. So that's the experiment that's shown in test here. So here's our evolutionary time here up to 60,000. And here's the number of moves on average that it took a male to find a female. By halfway through the experiment, any given male would find a female with a frequency of less than 50 moves, right? So the frequency in which males and females are finding one another and producing offspring is going up, right? Which is what you would expect, right? You have the evolution of communication now, where the females are modifying the evolved behavior of the males, and the males are evolving to respond appropriately to signals in the environment. In the control case here, they reran the experiment, but they simply turned off the input layer of the males. As you would expect, evolution can't make as much progress now because the females cannot communicate to the males. But up until this point, we can see that the males were actually doing a better job than the males in the original experiment. Why?
They
waiting for something. What is the something?
An input.
An input, right? They're not waiting for a signal. So this is one of the tricky things about the evolution of communication and language is there need to be two things that happen, right? You need to have the senders or the broadcasters send out the right signal at the right time, and for the receivers, in this case the males, to do the right thing when they hear the right signal, right? You need both to do the right thing. In this period here, in this experiment, the females are evolving to emit signals, and if males just happen to do the right thing in a few cases, then communication can get started. But it takes a while for that process to get going. What do you think these males are doing here in the control case? What behavior are they probably exhibiting? Go forward, right? If you can't hear, that's the best thing to do. Okay. We've just got a few minutes left, so we'll just have a look at a few more of these. Here's a very fancy animation of this evolved female signaling and male response pairing. So the female emits 0, 0, 0. Suddenly a male enters her territory. She changes from this signal to this signal, which the male either doesn't listen to or just continues to move forward. The male arrives on the same row. She changes her signal. The male turns right. She goes back to emitting the signal 1, 0, 1. The male moves forward, and they produce 2 offspring. Right? Here's another example of this. So now the male is coming in from the northwest. The female emits the signal 0, 1, 1. The male continues to move, reaches here. She emits the signal, which means turn left. The male turns left, which looks like a problem. Remember that the female, however, can see, quote unquote, where the male is and where the male is pointing. So she can see that he's pointed in the wrong direction, so she continues to emit the signal 1, 0, 1. So the male continues to turn left, makes 3 left turns, and now starts to head straight because she now says, all right, you're on the right heading to move towards me. Make sense? Okay. Turns out in this experiment, we got the evolution of communication where the females emitted these 2 different signals and the males responded appropriately. It turns out that there is a more sophisticated language that can evolve between males and females in this simplified experiment, in this simplified environment. We've run out of time, so we'll look at that more sophisticated signaling strategy on Thursday. You have a quiz due tonight, and that's it. We'll see you Thursday. Thank you.